Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to discuss some examples of symmetries and conservation laws, that how we derive these conservation laws or constants of motion, and how we use them to understand the dynamics of a system. We have been discussing about symmetries and the corresponding conservation. We have looked at Noether's theorem. We have discussed the integrals of motion and how to find out the integrals of motion. Here I am going to take some examples. The first example that I have is the spring connected bar on a horizontal frictionless table. You can see this bar of mass m, moment of inertia about the center of mass as I g and length L. I consider this coordinate system x y, which is located at the fixed point O of the horizontal table, and this point A, the end A of the bar is connected to the point O by a spring. For this bar, the generalized coordinates are 3: the position of the center of mass, the positional coordinates x g, y g, and the orientational coordinate theta, which is measured from the x axis. The kinetic energy of the bar can be written like this: straightforward, half mass times velocity square, here velocity of the center of mass square. So, kinetic energy of the center of mass plus the kinetic energy of rotation about the center of mass, half I g theta dot square. That is the kinetic energy. The potential energy expression is only because of the spring, and that is given by half k times length of or extension of the spring. I have considered a spring of 0 free length. Therefore, the force that acts or the extension that we measure to calculate the kinetic energy will be the distance O A, and that will be given by x a square plus y a square, where x a and y a are the coordinates of point A. We can write the coordinates of point A in terms of the coordinates of center of mass, which are our generalized coordinates, and theta, which is also a generalized coordinate, the orientational coordinate. In this way, and if I substitute these expressions of x a, y a in the expression of the potential energy, spring potential energy, then I obtain this expression of the potential energy function in terms of our generalized coordinates. The Lagrangian given by kinetic energy minus the potential energy is given here. So, this is our Lagrangian. We consider a transformed Lagrangian. What I am trying to do is, I am trying to find out an infinitesimal symmetry of this Lagrangian. Let us see if I succeed. I write down a new Lagrangian in terms of the new coordinates x g tilde, y g tilde and theta tilde. I have to find out a transformation between x g y g theta to x g tilde y g tilde theta tilde, such that this transformation, which will be as a function of a parameter, the transformation will be a function of parameter sigma. When sigma equal to 0, this transformation should be identity. Consider this transformation for the positional coordinates of the center of mass. If you look at the transformation carefully, you will notice immediately that this is nothing but the rotation matrix in a plane, where I have dropped the third row and the third column of the rotation matrix, because our there is no change in the z coordinate of the center of mass. Sigma is this parameter. If I put sigma as 0, you will notice that the transformation becomes identity. There is another transformation for the orientational coordinate theta. Theta tilde is theta plus sigma, and if you put sigma as 0, you get back theta tilde as theta. So, identity transformation. So, there is only a shift in the theta coordinate, whereas the rotational coordinate has a the positional coordinate of the center of mass has a rotational transformation. I have written here the complete expression of x g tilde. I have opened up the matrix product, and from here I can find out the velocities, because I need it for the kinetic energy. Similarly, for y g tilde in terms of x g and y g, I derivate that with respect to time to get the velocity in the y direction of the center of mass. Similarly, I derivate theta tilde, and that will be equal to theta dot only, because sigma is a parameter, it is a constant. Now, I substitute this transformation in my new Lagrangian, the L tilde Lagrangian, and I find, if you work this out, this detail I will leave to you. If you work this out, if you substitute these expressions of x g tilde dot, if you substitute these expressions in the new Lagrangian, the transformed Lagrangian, you will obtain the same Lagrangian as our original Lagrangian. In other words, I have found an infinitesimal transformation. I have found, actually this transformation is a finite transformation, but then it will always be an infinitesimal transformation as well. So, the Lagrangian is invariant under this transformation. Therefore, now from Noether's theorem we have this result that any infinitesimal transformation of the symmetry of the Lagrangian, any infinitesimal symmetry of the Lagrangian indicates that there is a conserved quantity. We have to find this conserved quantity now, and that will be our next task. To find the conserved quantity, we had discussed these steps before in a previous lecture. We first find out the generalized momenta. The generalized momentum vector is the partial derivative of the Lagrangian with respect to the generalized velocities, and if you do that, then it is straightforward to see that the velocities the generalized momentum vector is given by m x g dot, m y g dot and I g theta dot. Then we have to find out the infinitesimal generator of the transformation, and that is determined by taking a partial derivative of the transformation with respect to sigma and putting sigma equal to 0. Now, I have rewritten those expressions of the transformation, the expressions of the transformed coordinates of the center of mass. Here I will we also have the orientational coordinate transformation. We have to just derivate this with respect to sigma and put sigma equal to 0. You can check this very easily, that when I do a partial derivative of this with respect to sigma and put sigma equal to 0, the first term I have is cosine sigma, that gets derivated to minus sine sigma, and when I put sigma equal to 0, this vanishes, whereas this term when derivated will give me cosine sigma, and when I put sigma equal to 0, it gives me 1. Therefore, I have minus y g as the first term of this infinitesimal generator. Similarly, you can show that x g is the second term of the generator, and the third term is straightforward, del del sigma of this will be 1. And the conserved quantity, as per our previous discussions, is nothing but the generalized momentum vector dot the infinitesimal generator of the symmetry transformation. And this is our generalized momentum, this is our infinitesimal generator. If you take a dot product, you obtain this minus m x g dot y g plus m y g dot x g plus I g theta dot. This is a constant of motion, this is an invariant of motion or a conserved quantity. And if you notice a little carefully, this is nothing but the angular momentum of the system of the bar about that fixed point. And why do we have angular momentum conservation? Because the spring force always passes through that point O. Therefore, we have now been successful in finding out the conserved quantity or the constant of motion for this system. Now, this is one constant of motion which we obtained by finding out this. This was of course a task which may or may not succeed or may be quite difficult. Now, difficulty levels can vary. You may be able to see this transformation very easily, or maybe you have to work out, but these things will have to be searched for, and a lot of analysis can go into searching for such infinitesimal symmetries of the Lagrangian. This is one. The second symmetry or observation that we have is the Lagrangian is not explicitly time dependent. In other words, the partial derivative of the Lagrangian with respect to time is 0, and that immediately tells us that the Hamiltonian is a conserved quantity, which we have discussed before. To find out the Hamiltonian, we find out the generalized momentum, which we have done a few moments ago, and the Hamiltonian, if you use this expression, you can easily find that the Hamiltonian is this. And because if you notice, if you have already noticed this, that the kinetic energy is homogeneous in degree 2, that means we have only T2 terms in the kinetic energy. And we have also seen this, that if we have only T2 terms in the kinetic energy, then the Hamiltonian is the total energy of the system, total mechanical energy. In other words, it is kinetic energy plus the potential energy. We have kinetic energy plus the potential energy. Therefore, the total energy of the system is conserved. So, we have two constants of motion for this system. Next, we will look at this classic example of a spinning top. We will look at the dynamics of a top. First, we identify the generalized coordinates. These things we have discussed many times earlier. A top is a symmetric object. Therefore, we can very cleverly find a coordinate system or set a coordinate system which is not body fixed, yet the moment of inertia tensor is constant in this frame, and that frame I have drawn in brown. The z axis of the frame, the lowercase z axis of the frame is the axis of symmetry. X axis of the frame is found as a cross product of the capital Z and the axis of symmetry, and y axis completes the right handed coordinate system. The generalized coordinates in this case are psi, theta and phi. This is a motion, this is the motion of a top is a motion with a fixed point in inertial space. Therefore, we can do away with only the orientational coordinates. Psi is the angle that is made by this lowercase x and the fixed inertial frame x. This is psi. Theta is this angle, it is the angle between the axis of symmetry and the vertical inertial frame axis, and phi is the spin coordinate. So, phi dot is the spin angular speed. Theta dot, you may recall, is the nutational angular velocity, and psi dot is the precessional angular velocity. The Lagrangian can be written very easily as half omega dot IB omega. What is IB? IB is the moment of inertia tensor written about the point B, and this is typical of when a body is rotating or moving with a point fixed in inertial space. We can write down the total kinetic energy only using the angular velocity. This we have discussed before. Therefore, the kinetic energy part is 1/2 of omega dot IB omega, and the potential energy is because this thing is in a uniform gravitational field. We have to find out the capital Z, the horizontal this vertical distance. So, this vertical distance, and what I have here is this length OB is L. Therefore, the potential energy is mgl cosine theta measured with the ground as the datum. The ground is the datum. Therefore, we have kinetic minus the potential energy term, that is the Lagrangian, and once I have been able to write down the Lagrangian, I have to find out this explicit term, the terms explicitly. Here I have used that lowercase x y z frame to represent everything. So, omega, the angular velocity of the top, can be written in terms of the nutational angular speed, this theta dot I cap, plus a component of the precessional angular speed psi dot in the y direction, and in the z direction or the k cap direction, the axis of symmetry, we have a component of the precessional angular speed and the spin. This we have discussed before, how to express omega in this frame lowercase x y z. With that and the definition of the moment of inertia tensor about that point B, B is the ground point where the tip of the top is fixed. I have considered I naught, this moment of inertia tensor is written in this frame x y z, which happens to be a principal frame. And in this frame, as I have discussed just now, the moment of inertia tensor is a constant. I have considered I naught as the moment of inertia about x and y axis passing through B, and I is the moment of inertia about the axis of symmetry. So, this is a symmetric body, therefore, we expect that moment of inertia about x and y, which are orthogonal to the axis of symmetry, must be the same. With that defined, we can now write down the Lagrangian explicitly in terms of the generalized coordinates and their rates, and it is shown here. This is our Lagrangian. You will immediately notice there is no occurrence of psi or phi. We have psi dot, we have phi dot, we have theta dot, and we have theta, but we do not have psi and phi. Therefore, psi and phi are cyclic coordinates, and corresponding to every cyclic coordinate there is a conserved momentum, generalized momentum. The generalized momentum or momentum conjugate to psi is given by del L del psi dot, as we have discussed before, and you can very easily compute this from the Lagrangian. And this is a constant of motion, this is a constant, therefore, I will say that this is some constant A. Similarly, the momentum conjugate to the coordinate phi, which is p phi, is defined as del L del phi dot. Again, we can calculate very easily, this expression is given by this, and this is also a constant of motion, and I have named it as B. Now, using these two expressions, this term you will find here, therefore, this is nothing but B, and from there taking B cosine theta, this whole thing on the right hand side, I can define psi dot, the precessional rate, in terms of A, B, I naught and theta. Thus, we find that the precessional rate is a function of theta, other things are constants. The next thing we notice is the Lagrangian is time independent, explicitly time independent. There is no explicit time dependence in the Lagrangian, therefore, del L del T is 0, which implies the Hamiltonian is constant, as a conserved quantity, it is a constant of motion. And if you notice carefully the Lagrangian, it is the kinetic energy part, it is quadratic in the generalized velocity, it is homogeneous of degree 2 in the generalized velocities. The kinetic energy part is homogeneous of degree 2 in the generalized velocities. Therefore, we expect that the Hamiltonian is nothing but the total mechanical energy of the system. Hamiltonian is obtained as, this is straightforward thing to write, is the kinetic energy plus the potential energy of the system. Therefore, the Hamiltonian is the total mechanical energy of the system, which is conserved, it is a constant of motion. Here I can replace the psi dot which I wrote just now, I found just now, I can replace this psi dot and obtain this expression. Now, you will also notice that this term b square by I, this is also constant, b is constant of course, and I is also constant in this frame. Therefore, I can take it to the other side with and combine with the total mechanical energy E to define a new energy term, which I call E prime, as I have shown you, and E prime is a constant, it is a constant of motion. So, what do we have? We have now 3 integrals of motion or 3 constants of motion. The first one is obtained from the conjugate momentum corresponding to the coordinate psi. The second one is the conjugate momentum corresponding to the coordinate phi, and third is the energy conservation. These 3 equations involve psi dot, phi dot and theta dot, etc., and these therefore suffice to solve for the system. You have to start from some initial condition and you can numerically integrate these things to these equations to determine the motion starting from these initial conditions. But we are going to do a qualitative treatment, we are going to understand the dynamics qualitatively. For that, let us define u as cosine theta in the condition 3. You will notice that the condition 3 is an equation only involving theta, there is nothing else, the other coordinates do not appear in that. Therefore, we can think of something interesting from here, because this is a standalone equation, and let us see what we can say from this equation. To do that, as I have defined u as cosine theta in condition 3 in equation 3, and I can define I can find out theta dot by derivating that. U dot will be minus sine theta into theta dot, and sine theta can again be written in terms of cosine theta, etc. All those things have been done, and I leave it to you to check these details. You can finally express equation 3 in the form I have written as equation 4 by using this substitution, u is equals to cosine theta. Right. Now, let us interpret this equation, this constant of motion or this integral of motion. Now, as the motion proceeds, this quantity is going to be 0. We have come across this structure of an equation even in central force motion, where we are discussing energy, and we can interpret the first term half u dot square as kinetic energy and the rest of it as potential energy or some effective potential energy. And this half u dot square, this in a way reflects the nutational kinetic energy. Therefore, this theta dynamics of the nutational angle theta, and this kinetic energy plus the effective potential energy must be equal to 0, and this kind of analysis we have also done in central force motion, and we had drawn that effective potential and interpreted so many things out of there, and that is the same thing we are going to do here now. If you write out the potential energy as a polynomial, if you simplify, expand and simplify the potential energy, effective potential energy term, you will obtain this cubic equation. The first thing to notice is that the highest degree in u cube comes with a negative sign. What is the implication of this? If you take u towards positive infinity, though I must mention here one thing, u is equal to cosine theta. This was our definition, but algebraically the potential energy term, let us try to first understand the behavior of this cubic polynomial, and in that I will not make any restrictions on u, choice of u. If I take u to positive infinity, then the cubic term will be the dominant term, and you will have this function v effective goes to minus infinity. And if you take u to minus infinity, v u goes to plus infinity. This is the first observation we can easily make. Now, if you plot this function v effective, then you will first notice that there are some forbidden regions. Of course, u cannot be greater than plus 1 or u cannot be less than minus 1, because cosine theta, then theta will become imaginary, real theta will not exist. Therefore, these regions are forbidden. Now, just now I have mentioned this, that in the limit u going to plus infinity, effective potential goes to minus infinity, and if u goes to minus infinity, therefore, the effective potential goes to plus infinity. In other words, the nature of this effective potential is something like this, that as u goes to plus infinity, v goes to minus infinity, and as u goes to minus infinity, v goes to plus infinity. This is the first observation. Second thing you can notice is, if you evaluate the effective potential energy at plus 1 or minus 1, that means at these 2 points. If you evaluate the effective potential energy at these 2 points, you will get this expression A minus plus B whole square by 2 I naught square. Minus comes for at plus 1 and A plus B comes at u is equals to minus 1, and this must be greater than, this is a positive or 0. In other words, you can think of the curve something like this. It goes to minus infinity as u goes to plus infinity, and when u goes to minus infinity, this potential goes to plus infinity, and at these 2 points plus 1 and minus 1, these are positive. If you evaluate this potential energy function at u equal to 0, you will get this expression, and from here it may be difficult to exactly understand the sign of this quantity, because it can go negative like as I have shown, or it may also be like this, where this is greater than 0. Now, what are these points? Let us try to understand these points where the effective potential goes to 0. If the effective potential goes to 0, and because the sum of the kinetic energy and the potential energy must be 0. If the effective potential goes to 0, implies that kinetic energy must be 0. If the effective potential energy is positive, if this is positive, for example, here it is positive, kinetic energy is always positive, and if the potential energy is also positive, then that can never be equal to 0. Therefore, these things are unphysical, these branches are unphysical. Therefore, the physically valid or acceptable potential energy values lie only within this region where it is negative, and this is same as that we found in the case of central force motion. The bounded orbits have negative energy, unbounded have positive energy, but here positive energy does not mean anything. Okay. So, here we have the negative part which is physically acceptable, and then if we ask the question what happens at these points where the potential energy goes to 0, then the kinetic energy also goes to 0, as we have just now seen. In other words, the system will oscillate between these two limits. The system will oscillate between these two limits, just like a ball in a potential, in a concave upwards potential oscillates. In the same manner, this system is going to oscillate between these two angle limits. Now, I can read out those angle limits from this definition of u. This is the nutation range, and these two limits must be on the positive side, because for a physical top, theta must be greater than a certain positive, I mean it should be less than pi by 2, definitely less than pi by 2, because if theta is pi by 2, that means the top is has already touched the ground. Therefore, these two angles must be between 0 and pi by 2, definitely much greater than less than pi by 2, it should be much less than pi by 2. In other words, this lower bound should be much away from 0, u equal to 0, because if it touches the ground, the top will be called unstable, it has fallen off. So, this is the nutation range for a physical top, and this picture should be clear that the top oscillates between these two limits, just like a ball in a concave dish will oscillate. What do we understand by this point? U is equals to 1. U is equals to 1 implies theta equal to 0, that means the top is completely upright, it is an upright top. The axis of symmetry is coincident with the capital Z, that means it is vertical. You might have seen that sometimes if you give a very high spin to a top, it remains upright and does not precess or nutate, it remains upright. We will analyze this situation. Therefore, our top, the configuration of the top is such that u is equal to +1, and if it is not to nutate, if it is not to oscillate, then I must have this picture for the effective potential energy curve. Why this picture? Because as I have mentioned, physically acceptable potential energy values are negative. Now, that means this curve cannot go down, it must be this way, and in that case, if when I gave you that ball example in a concave dish, the system will remain at this lowest potential energy. It cannot move, definitely it cannot move to the right because it is a forbidden zone, and it will not move to the left because then potential energy will go positive, it is not allowed. Then the top is going to remain with its axis of symmetry completely vertical and it is not going to move out from there. Let us look at that condition. There can of course be another condition which satisfies this upright and no nutation. It is this brown curve that also satisfies that. And if you again look at the particle analogy or the ball analogy, now the ball is on a convex upwards dish and maybe it can roll down, because here we have potential energy as negative. It can roll down if it is disturbed from here. It cannot go to the right, of course, it is forbidden, but it can go down this way. We will first analyze this situation. If the potential energy is 0, as we have seen here, the potential energy value, the effective potential energy value is 0, which means this can happen only when A equal to B, only then you can have one of these values as 0, which is at +1, we will have it as 0, and the other at -1 it will be something positive. As we can see, this goes up and there it will be positive, but at +1 it is going to be 0, and therefore, we conclude that A must be equal to B. These two constants must be the same. And here, because the potential energy is 0, this whole thing is 0, therefore, u dot is 0, as we have noted, and this quantity, if you now compute, you will find that this is greater than 0, as you can see here. If you calculate the slope of the potential energy curve at +1, u is equals to +1, and that is 0, slope is 0 as per our picture of the potential energy variation with u, it must be 0, and that gives us that the total energy, this detail I leave to you to check, that the total mechanical energy must be equal to the spin kinetic energy and the potential energy. Note that the potential energy is being measured, the datum is the ground, and when it is upright, the potential energy is really mgl, and it is only spinning, there is no nutation, there is no precession, therefore, the kinetic energy expression is only half I times phi dot square. So, the top is completely upright, this is the total mechanical energy. What else do I observe from this curve? We also observe that the curvature of this curve, or the double derivative of the potential energy, effective potential energy function at +1 is positive. If I use that, and this detail again I leave to you, you can show that the spin angular rate must be greater than a quantity which is shown here, and this condition of the top is known as the sleeping top. It appears absolutely stationary, the top has its axis vertical and it is stationary, it is as if it is sleeping. So, we call it a sleeping top, and this is a stable sleeping top. If you again take that analogy of the particle in a convex dish, if the particle is left here, it will remain there, even if it is disturbed, it will come back to it. So, if you disturb this sleeping top, it will again come back very quickly to its vertical position, but for that the spin has to be greater than this quantity, which you can determine. Look at the other situation, where the other things roughly remain, this definitely remains same. Here this is negative, this quantity becomes negative, or it can also be positive, this can be like this. Therefore, we cannot say for the sign unless we have all the parameter values, and the total mechanical energy turns out to be this, which is again correct, but the double derivative of the potential, that is negative. This is an unstable sleeping top, because if I disturb, if you use that analogy, particle analogy, if you leave a particle here and slightly if you disturb it, it is definitely going to go this way, it cannot go to the right because it is forbidden, it will go here and it will oscillate. if it actually with this curve, if it will hit the ground somewhere and it will fall down. More or less the qualitative behavior of the top is therefore found from this analysis. Let me just summarize. We have looked at some examples of systems where I have shown the application of infinitesimal symmetries and constant determining the constants of motion using them, and finally qualitatively finding out the dynamics of a system. With that I will conclude this lecture.